From the Bristol Beaufighter and de Havilland Mosquito to Germany's Bf-110, Ju-88, and He-219, these twin-engine night hunters turned darkness into a killing field. Here's how radar, guns, tactics, and airframes evolved into the deadliest nocturnal interceptors. Messerschmitt Bf-110 night fighter variants began as adaptations of a failed daylight heavy fighter, repurposed to hunt bombers after dark. Its twin engines offered endurance, while space for radar operators made airborne interception practical. Early installations were crude and drag-inducing, yet effective enough to anchor Germany's initial night defense. The aircraft established basic interception workflows, later refined by more specialized designs during the war. Bristol Beaufighter emerged from a long-range fighter concept and quickly proved well-suited for nocturnal combat. Heavy forward armament allowed short, decisive firing passes, while its stable platform aided radar-guided approaches. The type became the backbone of RAF night interception during critical bombing campaigns. Its adaptability supported multiple marks and roles, without sacrificing night fighting effectiveness across varied theaters and evolving threats throughout the conflict. Junkers Ju-88CG transformed a versatile bomber airframe into one of the most numerous night fighters of the war. Strong performance margins supported radar arrays and heavy cannon fits without severe penalties. Continuous upgrades kept the design relevant as Allied tactics evolved. Its balance of speed, range, and payload made it a mainstay of German night operations through late-war defensive phases in Europe. Douglas P-70 Havoc represented the United States' early attempt to field a radar-equipped night interceptor. Converted from the A-20 attack aircraft, it provided valuable operational experience rather than decisive performance. Limitations in speed and ceiling restricted its effectiveness against advanced threats. Even so, the type helped train crews and refine American night fighting doctrine before purpose-built designs became widely available later in the war years. Petlyakov P-3 adapted a high-speed bomber derivative into a Soviet night fighter solution under wartime pressure. Emphasis remained on range and basic interception rather than advanced electronics. While radar integration was limited, the aircraft filled a defensive gap during critical periods. Its service reflected improvisation and the Red Air Force's urgent need for night-capable fighters on multiple fronts during the conflict against persistent bombing threats. AI MK-4 was the RAF's first practical airborne interception radar, enabling night fighters to detect bombers beyond visual range. Early sets were bulky and limited in resolution, requiring close coordination between pilot and operator. Despite reliability issues, it marked a decisive shift from visual searches to electronic interception and shaped early British night fighting tactics. During the early war years, AI MK-8 represented a major leap with centimetric radar using shorter wavelengths for sharper target definition. Smaller antennas reduced drag and improved aircraft performance. Crews could now achieve more accurate positioning in cluttered airspace. This technology significantly improved interception success rates and became standard for advanced Allied night fighters later in the conflict across multiple operational theaters, worldwide operations. Liechtenstein BC designated early German airborne interception radars fitted to night fighters during the initial defense phase. Operating at longer wavelengths, the system required prominent external antenna arrays. These installations increased drag but enabled controlled approaches in darkness. The equipment integrated tightly with ground control networks and defined standard Luftwaffe night interception procedures during the mid-war period overall doctrine. Liechtenstein SN2 replaced earlier sets to counter Allied jamming and improve detection reliability. Operating on lower frequencies, it offered longer detection ranges but required larger antennas. The system restored German interception capability during heavy bombing periods. Its introduction forced tactical adjustments on both sides as electronic warfare intensified in the night skies over Europe and surrounding operational theaters' overall impact. FUG-350 Naxos was a passive receiver designed to detect emissions from Allied radar systems. Rather than searching for aircraft, it homed on enemy electronic signals. This capability allowed night fighters to cue intercepts without active transmission. Its effectiveness varied, but it highlighted the growing importance of electronic intelligence in aerial combat during late-war defensive operations and countermeasures development. Monica tail warning radar was an Allied defensive sensor alerting crews to approaching aircraft from behind. Mounted to monitor the rear hemisphere, it aimed to reduce surprise attacks. While conceptually valuable, emissions could be detected by enemy receivers. The system demonstrated how defensive electronics could inadvertently expose aircraft positions during night operations over contested airspace environments throughout the war period overall. Schräge Musik upward-firing cannon allowed night fighters to attack bombers from below, exploiting blind spots in defensive coverage. Mounted at an oblique angle, the guns enabled sustained firing without entering turret arcs. This method reduced return fire risk and proved highly effective once crews mastered positioning and timing during nocturnal interception missions. 20mm cannon batteries formed the standard armament of many night fighters, balancing destructive power with controllable recoil. Multiple guns increased hit probability during short firing windows. These weapons were effective against bomber structures without excessive ammunition weight, allowing aircraft to retain performance while delivering decisive damage in carefully timed engagements. Overall effectiveness. 30mm Mk-108 heavy punch emphasized destructive impact over accuracy in late-war German night fighters. The weapon delivered devastating damage with few hits but had limited velocity. Crews relied on close-range firing opportunities, making it well-suited to surprise attacks where brief exposure and rapid disengagement were essential for nocturnal interception missions. Turreted interception layouts appeared on selected Allied night fighters, aiming to provide flexible firing arcs against maneuvering targets. Powered turrets allowed engagement without precise nose alignment. However, added weight and complexity reduced overall performance. These designs reflected experimentation with bomber-destroyer concepts rather than a universally successful solution during wartime development and operational evaluation. Forward bomber-destroyer gun packs concentrated heavy firepower in the aircraft, nose for direct interception passes. This configuration simplified aiming and maximized damage in seconds-long engagements. It favored head-on or stern attacks, guided by radar cues. The approach suited aircraft with strong structures capable of absorbing recoil and stress during repeated combat interceptions overall. Radar-guided firing approach and range discipline defined how night fighters converted detection into kills. Crews closed to prescribed distances before opening fire, reducing wasted ammunition. Coordination between radar operator and pilot was critical. These procedures emphasized control and precision, shaping standardized engagement methods across Allied and Axis forces throughout the war under varying operational conditions. Pilot and radar operator division of labor define night fighting effectiveness in twin-engine aircraft. The pilot focused on aircraft control and visual acquisition, while the radar operator managed detection, tracking, and verbal guidance. This separation reduced workload during complex interceptions. Clear communication rhythms were essential, as delays or misunderstandings could break contact in darkness under combat stress conditions night. Ground-controlled interception vectoring linked radar stations with airborne crews to guide fighters toward incoming bombers. Controllers calculated headings, altitude changes, and timing before handing targets to onboard radar. This system compensated for limited aircraft sensors early in the war. Its effectiveness depended on communications reliability and uninterrupted radar coverage across defended regions under sustained operational pressure and heavy demand. RAF Cat's Eyes and bomber stream interception methods focused on penetrating dense formations rather than isolated aircraft. Night fighters were directed into bomber streams where targets were plentiful. Visual cues, exhaust flames, and shadowing aided final acquisition. This approach maximized interception opportunities during mass raids while reducing time spent searching empty airspace under blackout conditions and heavy defenses at night. German Kammhuber line-style layered defense concepts organized airspace into controlled zones monitored by radar and searchlights. Fighters were assigned specific boxes to intercept intruders. Centralized command reduced confusion but limited flexibility under saturation attacks. As bomber numbers increased, the system became strained, forcing tactical adaptation and decentralized interception methods during prolonged night bombing campaigns over major industrial regions repeatedly. Closing geometry, including stern, beam, and underside attacks, shaped how night fighters approached targets. Stern attacks favored radar alignment, while beam approaches reduced defensive fire exposure. Underside positioning exploited blind spots. Choice depended on aircraft armament and situational awareness. Mastery of geometry increased survival rates during brief firing windows in darkness against heavily defended bomber formations at night altitude levels. Disengagement using darkness, cloud, and speed management was as critical as the attack itself. Night fighters avoided prolonged exposure after firing. Cloud layers offered concealment, while speed changes broke pursuit. Crews relied on discipline rather than aggression. Successful withdrawal preserved aircraft and personnel for repeated sorties across long defensive campaigns during sustained nighttime air defense operations over occupied territory often. De Havilland Mosquito NF combined speed, range, and a wooden airframe into one of the most effective night fighters of the war. Its performance allowed interception without heavy reliance on ground control. Advanced radar fits integrated cleanly. The aircraft excelled as both interceptor and intruder, maintaining effectiveness across evolving night combat roles throughout prolonged operations against diverse targets in multiple theaters worldwide during conflict. Northrop P-61 Black Widow was the first American aircraft designed specifically for night interception. Its large airframe housed radar, heavy armament, and multiple crew positions. Stability favored controlled engagements. Although late to combat, it set standards for post-war all-weather fighter concepts. Operational experience highlighted strengths and limitations under demanding conditions encountered during early deployment phases overseas, with crews adapting procedures quickly in service use. Junkers Ju-88G represented the peak evolution of Germany's versatile night fighter family. Improved engines and refined aerodynamics enhanced performance. Heavy armament and advanced radar made it formidable. These variants carried the night defense effort during intense late-war bombing campaigns, despite increasing resource shortages and operational pressure from Allied air superiority across multiple fronts in Europe until war's end approached rapidly overall. Bristol. Viewfighter late marks shifted toward fast intruder missions as defenses matured. Improved engines increased speed and range. Crews targeted airfields and patrol zones at night. The aircraft's rugged design supported aggressive operations beyond pure interception roles. This flexibility extended its relevance despite newer competitors and changing operational priorities late in war across coastal and continental theaters under varying threat conditions during service period. Lockheed P-38M Night Lightning adapted a high-altitude fighter into a radar-equipped night interceptor. Twin booms provided stability and space for sensors. Limited numbers saw service. The type offered valuable insight into adapting fast fighters for nocturnal operations without compromising daytime performance characteristics. Its experience informed later all-weather developments within United States aviation planning circles after wartime evaluation periods concluded successfully by analysts. Heinkel, a Tu-19. Uhu was one of the few aircraft designed from the outset as a dedicated night fighter. It integrated radar, heavy armament, and crew ergonomics into a single airframe. The design emphasized climb, stability, and pilot visibility. Operational use was limited, but the aircraft demonstrated what a fully integrated nocturnal interceptor could achieve under ideal development conditions during late wartime evaluations periods. Dornier Du 217J and N variants adapted a heavy bomber platform into a night interception role. The aircraft carried radar operators, large fuel loads, and substantial gun installations. Size limited agility, but endurance supported long patrols. These versions filled an interim gap, contributing to night defense before more refined specialized fighters entered wider service during late-war transitional operational periods. Overall effectiveness. Nakajima J1N1S Gecko began as a reconnaissance design before conversion into a night fighter. Japanese crews fitted upward, firing guns to counter bomber threats. Lacking sophisticated radar, interceptions relied on visual cues and ground guidance. Despite limitations, the aircraft achieved notable successes and demonstrated adaptive solutions under constrained technological and industrial conditions during prolonged defensive night operations across multiple island theaters of war. Kawasaki Ki-45, Toryu Night Fighter Fits, transformed a twin-engine interceptor into a bomber hunter. Modifications focused on armament changes and crew coordination. Performance remained adequate rather than exceptional. The type served as a practical response to increasing night raids, reflecting Japanese emphasis on rapid adaptation rather than purpose-built specialization under wartime pressure and limited access to advanced electronic systems. Overall context. Mitsubishi Ki-46 night fighter conversions adapted a fast reconnaissance aircraft for interception duties. Speed-aided approach, but limited armament reduced lethality. Radar integration was minimal or absent. These conversions were stopgap measures, highlighting the difficulty of countering nocturnal bombing without dedicated platforms or mature electronic support systems during late-war defensive efforts under resource shortages and escalating air pressure from sustained Allied raids. Douglas P-61, as a design for night benchmark, illustrates the maturation of nocturnal interception concepts. Purpose-built layout integrated radar, crew stations, and heavy weapons from inception. The aircraft emphasized endurance and control over speed. Its design philosophy influenced post-war all-weather fighters, shaping doctrines beyond the Second World War period and remained relevant in early Cold War interceptor planning frameworks. Worldwide overall legacy. Mosquito NF influenced post-war night and all-weather doctrine by proving that speed, range, and onboard radar could coexist without turning the aircraft into a slow specialist. Air forces took from it the idea that a night fighter could also be a high-performance, multi-role platform. Training, crew coordination, and maintenance practices around radar sets matured in service, feeding directly into early post-war all-weather units and readiness standards in multiple air forces. P-61 provided a radar operator workflow template that many later crews recognized immediately. Its cockpit arrangement and crew roles formalized the division between flying, detection, and engagement decisions. Operators learned to manage contacts and handoffs under time pressure, while pilots learned to trust instruments and concise calls. That human systems pattern carried into early jet interceptors, squadron training, and ground radar integration for complex night sorties. He-219 and Ju-88G pointed to an integrated sensors plus heavy armament model, where electronics, crew layout, and weapons were treated as one package rather than bolt-ons. Both showed the advantages of designing around radar displays, power, needs, and firing geometry from the start. Post-war designers carried forward the lesson that interception success depended on integration as much as raw aircraft performance and field support under intense operational tempos. AI radar miniaturization trend pushed aviation toward true all-weather interceptors by shrinking antennas, improving reliability, and fitting advanced sets into faster airframes. As centimetric systems matured, aircraft could carry radar with less drag and fewer compromises. This enabled higher climb rates, better handling, and greater mission flexibility. The shift helped make radar a standard feature of frontline fighters rather than a niche, night-only add-on in haze and cloud. Night fighter tactics left modern intercept geometry and GCI routes that outlived the prop era. Controlled approaches, disciplined closure, and clear crew communications became codified procedures. Ground controllers and airborne crews developed standardized vectoring language and expectations about timing and altitude. Even as technology changed, the underlying logic of finding, fixing, and intercepting targets in poor visibility remained central for air defense across crowded nighttime airspace. Twin-engine layouts taught endurance, payload, and stability lessons that shaped early jet choices. Two engines offered redundancy over water or hostile territory and supported heavier electrical loads for radar. Larger airframes gave room for operators, fuel, and weapons, while stable handling aided instrument flying. Although single-engine jets later dominated, the trade-offs first proven by twins informed many early all-weather designs for longer patrol endurance,